Hello and welcome in today's video. In today's video, we are going to look at limits of functions. And a function is just a mapping from one set to another. So in this case, we say that let f of x be a function. And let a and l be real numbers. So we say that if f of x approaches L as x approaches A, but not necessarily equal to this particular value A, then we say that f of x has a limit L as x approaches A, and we shall denote that by the limit of f of x as x approaches A, which is equals to L. So in this particular case, this x can approach A from below, and is approaching A from below, or it can approach A from above. Now I'm going to package this as an example, whereby we are saying that consider the function f of x which is equals to 2x plus 3. Then the limit of this particular function 2x plus 3 as x approaches 2 is equal to 7. So you can be able to show that using a table, whereby you'll be picking values of x that are approaching 2 and also values of x that are approaching 2 from above and below. So for example, when you look at it, table number 1, these values of x, they are approaching 2 from below, and that's why I'm putting the negative here. Now the values I'm mapping in my table here. The first x is 1.9, the second one is 1.99, the third one is 1.999, continuing that way. So should you substitute these values in our function here, which is f of x here, that is substitute the value of x with 1.19, or 1.9, sorry, 1.99, 1.999, continuing that way up to the last one. These will be the output. For example, f applied on 1.19, f applied on 1.9, this is going to give us 6.8, and you can see we have 6.8 here from calculation. If you apply f on 1.99, it is going to give us 6.98. If you apply x on, or if you apply f on 1.999, this is going to give us this value. Now continuing that way, you realize that these are the values that are being produced here. Then if we add another value here, which is 1.999999, this is how many times? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So the pattern here, without even computing, it will be 6.9999 5 times, because this is 4 times. 2, 3, 4. Then you put an 8 at the end. Now this pattern is very clear that if you try to round off these values, that is this all the way to the last one, the answer will be equal to 7. That is, if you try to round off, that will give us 7. So in table number 2, we will be picking values of x that are approaching 2, but from above. That is on the right hand side of 2. Now in this case, you are picking the first value to be equal to 2.1. You can see 2.1 is slightly greater than 2. 2.101, it is slightly greater than 2. 2.001, it is slightly greater than 2. Continuing that way. So what will happen if you apply these values, or you apply f on these values? That is, you substitute your 2.1 here. So it means that you'll be able to apply f on 2.1, which is going to give us 7.2. If you apply f on 2.01, it is going to give us 7.02. If you apply f on this 2.001, it is going to give us this value, and you can be able to see the pattern. The first one was 7.2, the other one was 7.02, the other one was 7.002, and the other one is 002. You can see this is 1 time, 2 times, 3 times, 4 times. Even if you add another one here, it will be 0 5 times, then you put a 2, then 7 point. Those 5 zeros there, then you put a 2 at the end. And if you try to round off these values, you realize that this is approaching 7. So both these values of x that are approaching these two from below and from above, they are converging at this particular 7. And now we can conclude that the limit as x approaches 2 of 2x plus 3, it is equals this particular value 7. So in this particular case, our A is equals to, this is our f of x, and now this is our L. So that is one way in which you can be able to compute the limits of functions. That is, you pick values of x that are approaching that A from either below or above. But you realize that these would be tedious. That is, computation of all these would be tedious. Coming up with tables and all that, even some of the functions may be very complex. Now coming up with the tables will be difficult for you. So that brings us to our next topic, or subtopic, which is now the techniques of evaluating limits. The techniques of evaluating limits. And we shall start with the first one, which is now the direct substitution. So what happens in this particular case? You just plug in this value A into your function f of x. And now what you get, it will be now your limit. For example, this particular case, if you take this particular function, you let f of x be our function there, which is 2x plus 3. Then you can be able to say that the limit as x approaches 2 of this particular function f of x, which is 2x plus 3, it will be equal to, we just plug in this particular value 2 into the function f, and this will be equal to 2 multiplied by 2 plus 3. Clearly you can see that this is giving us 7. And also think of another function. This is number 1. Number 2, or Roman 2, you can think of an f of x which is equals to, you can think of a 4x squared plus 2. So in this case, what would be the limit as x approaches 1 of this particular function, 4x squared plus 2? This by direct substitution, and we normally indicate ds over this equal sign here, because the technique that we are applying there, it is direct substitution. So for this one, we just substituted this 1 in this particular function f, and what we get, it will be 4 multiplied by 1 squared plus 2, which is going to give us what? This is 1 squared, which is 1. 1 times 4, you get 4. 4 plus 2, you get 6. Now you'll be able to say that the limit of this particular function, 4x squared plus 2, as x approaches 1, it is equals to 6. And also proceed and have another function, Roman 3, which looks like this, whereby your f of x is equals to, and think of x squared plus 1 divided by x. So now what will be the limit of this particular function, which is x squared plus 1 over x, as x approaches maybe negative 1. So this one by direct substitution, which we need to indicate here after the equal sign, or on top of the equal sign there, it will be the same as what? You replace the x with negative 1. So this would be negative 1 squared plus 1. Then you divide by negative 1, which is going to give us what? 1, because we know that negative 1 squared is equals to 1. If you add it to 1 and divide by negative 1, so this will be just 2 divided by negative 1, which is just negative 2. And now this will be our limit as x approaches negative 1. So now next is example number Roman 3, whereby you are given your f of x as equal to 3x cubed minus x squared plus 2x plus 8. So you are told to evaluate the limit of this particular function, which is 3x cubed minus x squared plus 2x plus 8 as x approaches 2. So this by direct substitution, it means that you replace the values of x in the function here given by 2. This would be equal to 3 multiplied by 2 cubed minus 2 squared plus 2 multiplied by 2 plus 8. And if you compute that, using a calculator, this is going to give us what? 32. Can also be given a function like this, which is evaluate the limit of x squared minus 1 divided by x minus 1. And this is as x approaches 1. So this one, by direct substitution, we can write it down here. This is the limit as x approaches 1 of this particular function. That is x minus, or x squared minus 1 divided by x minus 1. So what will happen if you try to substitute directly here, or to use direct substitution? This is going to give us what? This will be 1 squared minus 1 divided by 1 minus 1, which will give us what? 1 minus 1 over 1 minus 1. And you know that 1 minus 1 is equal 0. So this means that it is going to give us 0 over 0. So 0 over 0 is undefined, because in mathematics we try to avoid as much as we can to divide anything by 0. Every number that is divided by 0 is always equal to infinity. So what is the implication here? It implies that here we cannot be able to use direct substitution to evaluate this limit. This indeterminate form, 0 over 0, tells us that there is a common factor between the numerator here, the numerator here and the denominator here. Because when you look at our function here, it is in fraction form, or it is in rational form. So the thing is, there is a common factor between the numerator and the denominator. Now, this brings us to another technique, which is technique number 2. Number 2 is what we call the factorization. Factorization. So what happens in factorization? We try to factorize. For example, in this case, you try to factorize the numerator and check whether you can be able to get common factors between the numerator and the denominator. So using the same function there, that is the limit as x approaches 1 of x squared minus 1 divided by x minus 1. This would be the same as what? This would be the same as what? Let me put this in this and so this limit as x approaches 1 of x squared minus 1 over x minus 1 will be equal to the limit as x approaches 1 of x plus 1 multiplied by x minus 1 divided by x minus 1. Because this x plus 1 multiplied by x minus 1, it is the factorized form of the numerator. I hope you recall this, that should you multiply a plus b multiplied by a minus b, this should always give us what? A squared minus b squared. So this numerator here, it is assuming this particular format. Now this means that the factorized form of it, which is what we have here. And now when you look at this numerator and the denominator here, this value is common, so you can be able to cancel it out. you realize that at the end you'll be presenting this limit or this particular function in a simpler manner, that is x plus 1, which can allow us to use what we call the direct substitution. The direct substitution here would imply that we are replacing the value of x with 1, which is going to give us 2. So the next example, that was example number 1. The next example, which is example number 2. So example number 2, we are taught to evaluate the limit of this particular function here as x approaches 2. So what will be the solution of this? We can try by direct substitution and see what we are getting. That is, this is the limit as x approaches 2 of x squared plus x minus 6 divided by x minus 2. So the direct substitution of this, let us see what we are going to get. It will be 2 squared plus 2 minus 6 divided by 2 minus 2. This would mean that this would be the same as what? 4 plus 2, which is 6. 6 minus 6, you get 0. The denominator will be 0, because 2 minus 2, you get a 0. So once again, we are getting the indeterminate form 0 over 0. So this tells us that we have a common factor between the numerator and the denominator. So when you look at the numerator, it is a quadratic equation. It is a quadratic equation, meaning that we can be able to factorize it. So for us to be able to factorize any quadratic expression, for instance, in this particular case, we look for two numbers such that when you multiply them, you get negative 6, but when you sum them, you get negative or positive 1. So in this case, we factorize. That's why we call this method factorization. Factorize x squared plus x minus 6. So in this case, the product will be equal to 6, and the sum of it will be equal to positive 1. So what are these numbers such that when you multiply them, you get negative 6, and when you sum them, you get positive 1. These numbers are negative 2 and 3. You notice that negative 2 plus 3, it is going to give us positive 1. But negative 2 times positive 3, we're going to get negative 6. Now this implies that the factorized form will be equal to x squared minus 2x plus 3x minus 6. So you can factor out, or between the first and the second terms, you can factor out x, because x is common there. What will be left there with it is x minus 2. The third and the fourth term, you can be able to factorize 3, or factor out 3. And if you factor out 3, you'll be left with x minus 2. So once again, this x minus 2 is common between this term and this term. So meaning that you can factor it out, that is x minus 2. And if you do that, you'll be left with x plus 3. So meaning that the factorized form of the numerator here, it is x minus 2 multiplied by x plus 3. So what does this mean? That our limit, that is this expression, they can be written as follows. That is the limit as x approaches 2 will be equal to, or is expressed as follows, that instead of having this, you replace with what you have here. And this is x minus 2 multiplied by x plus 3. You divide this by the denominator, and the denominator is x minus 2. So x minus 2. And now when you look at the numerator and the denominator, you notice that x minus 2 is common. So you can be able to cancel them out. So meaning that at the end of the day, you'll be left with the limit as x approaches 2 of x plus 3, which is going to give us, or by direct substitution, this would be 2 plus 3. Which means that you're just replacing the value of x with 2, which is what you have here. Now 2 plus 3, it is going to give us 5. So this means that the limit of this particular function as x approaches 2 is equals to 5. So the next example is Roman 4, whereby we are told to evaluate the limit as x approaches 1 of this particular function here, which is x cubed minus 1 divided by x squared minus 1. So what will be the solution here? So in this case, you realize that you can try direct substitution and see whether it is going to work. That is x cubed minus 1 over x squared minus 1. So this by direct substitution, it will be equal to 1 cubed minus 1 divided by 1 squared minus 1, which is going to give us what? 0 over 0. So 0 over 0 is undefined, so it is indeterminate. So meaning that there is a common factor between the numerator and the denominator. But now, since you cannot be able to factorize this numerator with a lot of ease, you can opt to use what we call the long division. That is, we can try to simplify this by the long division, whereby you take x cubed minus 1 divided by x squared minus 1. So what is going to happen here? If we try to divide the two, you realize that always consider the first term in the dividend. This is what we call the dividend, this is what we call the divisor. That what we obtain here at the top, it will be the quotient, and if you narrow down, you will be left with what we call the remainder. So, what is the first term in the dividend? What is the first term in the divisor? So you can take x power 3 divided by x squared. And if we simplify this, is going to give us x squared. So this x squared, it is now the value that you should multiply by the divisor, x, so that you can get a value or an expression with x cubed, because our interest is to eliminate this x cubed. Do you notice that this will be the same as what? What is x multiplied by x squared minus 1? This is equals x cubed minus x. So meaning that this will be x cubed here minus x. So if we subtract the two, the x cubed will be eliminated. So what is negative 1 minus x? This will be negative 1 plus x, because you know that minus will be equal to plus. So this can be written as what? X minus 1. So it's always good to start with a positive value and you go to the negative. So we've just written that. Do you notice that here we cannot be able to proceed further? That is, the degree of the remainder, this is a remainder, it is less than that of the divisor, which is x squared minus 2. So it means that this is your quotient, this is your divisor, this is your remainder. So if you go, I take you back to a simple case whereby you are given 7 divided by 3. 7 divided by 3, this goes how many times? 2 times because of what? 6. And the remainder is 1. And you can be able to express this in fraction form as follows. That is 2 and a third. And if you try to simplify this mixed fraction, multiply this times this plus this, which is going to give us what? 7 over 3. Now 7 over 3 is just the same as 7 divided by 3. Or 7 multiplied by 1 over 3. So the question is, can we be able to present this in that particular format? That is, can we be able to write this in this particular format as a mixed fraction, then we split it. So the implication here at this particular point, that is 1 over 3, you can be able to split it into 2, that is 2 plus 1 over 3. It will still be the same thing. Now this means that if I go back to my results here, this implies that this is the same as what? X, then the remainder, which is x minus 1 over x squared minus 1. That is the x, which is a quotient, then the remainder over the divisor. Now this means that this can be split as what? X plus x minus 1 over x squared minus 1. So this is easier compared to this. So instead of having this now here, we replace with what we have here. Now this implies that this will be the limit as x approaches 1 of x plus x minus 1 over x squared minus 1, which would be the same as what? The limit as x approaches 1 multiplied of what? X plus. So when you look at the second term here, you realize that the denominator can be factorized like we did before. So the factorized form of the denominator, it is x plus 1 multiplied by x minus 1. Once again, you notice that this will disappear, or we cancel with that one. So that you are left with what? The limit as x approaches 1 of x plus 1 over x plus 1. Which means that we can be able to use what we call the direct substitution. That is, in the case of x, we replace with 1. This would be 1 plus 1 over 1 plus 1. You can see we are replacing this x with 1 and this x with 1. So which would be equal to 1 plus a half. And 1 plus a half, it is 1 and a half, which is equal to 3 over 2. Now this will be our limit of this particular function, which is x squared minus 1 over x squared minus 1. I repeat, this is the limit of this particular function, x cubed minus 1 over x squared minus 1. That is the end of that particular technique.